Hi everybody, welcome to another offline video. Last time we stopped at section 7.3, now we continue at 7.4. Because we did not have enough time in class to go over everything, so we have to do some recorded video. We'll go over this section rather quickly. So the area of a triangle. So first, let K be the area of triangle ABC. We will not use A for triangle, A for area, because the triangle usually we have ABC, so we don't want to use A anymore. Right. The first and the most fundamental formula for the area of a triangle is just 1/2 base times height. So I have the height and then the base. So area is 1/2 base times height, which is 1/2 base and then height. And with trigonometry, we have a few more formulas for triangle. Now, if we are given the sine, angle, and the sine, for example, so when we are given a sine, two sides, so we know the length of those two sides and then the angle in between. This is called sine, angle, sine scenarios, and in that case the formula for the triangle is 1/2 AB sine C, or 1/2 BC sine of A, or 1/2 AC sine of B. So as you see, we have A, B, C all present, little a, little b, and angle C. Right. Next we have angle, sine, angle, or angle, sine, triangle. In this case, we have K equal to A squared sine B sine C over 2 sine A. So notice that in a triangle, if we know two angles, then obviously we'll know the other angle as well. So in this scenario, we have all three angles. So that's why we have sine B sine C over A sine A. So A squared then over sine A. So if we write with B squared then it will be divided by 2 sine B. And then the other two side of the other two angles, sine A, sine C. And then this, if we have C square, we will divide by 2 sine of C. And then the other two angles, sine A, sine B. Right. So it's like that. So and the last case is where we have the length of all three sides. When we are given all three sides, we're going to use what formula? The formula that we call the Heron Formula. This is called the Heron Formula, and this formula is more than 2,000 years old. So in this case, we let S, that is little s, it's not the area, it's just A plus B plus C divided by 2. And what we call S is the semi-perimeter. Meaning A plus B plus C is 3 sides, and then we divide by 2. In that case, the area given by Heron formulas is S minus A, S minus B, and S minus C. Let's do a couple of samples. Right. A painter needs to cover a triangular region (61 meters, 67 meters, and 72 meters. Now, a pen covers 70 square meters. How many cans? Will be needed? Right. So first, in this triangle, we have 3 sides, so we have to use the Heron's formula. First, we find the semi-perimeter. Little s is the sum of all of those 3. Right. 61, 67, and 72. We divide by 3. Sorry, by 2. That will be 100. And then the Heron Formula. S minus A, S minus B, S minus C. So we have square root. S is 100. S minus A, 100, minus B, 100, minus C. And that gives us the area. So we have square root, second square root, 100 times 100 minus 61, 100 minus 67 times 100 minus 72, and we have that much. And we have the square root already. So the area will be 1898.3. The area will be meter square. Right. Next, that's not the question. The question is how many can of pen will be needed. So 1 can cover 70 meters. Then if we need to cover 1898.3 meters square, how many can do we need? So that's just the ratio and proportional problem. We set up 1 over x equal to 70 times that, and just cross multiply. So we have 1898.3. I'm just going to drop the unit, because here if we can just cancel meter square and cancel the can, we don't have any numbers anymore. Anyway, cross multiply 70x, and so we solve for x. Take that number, divide by 70. So x is equal to 27.11. But notice that this is just happened in real life. Even though we only need 0.11 of a can, we always have to round up. We need 28, because it's supposed to have to be more than that. Whatever the answer is should be rounded up. So in that case, we need 28 cans. So the Heron formula gives us the area, and then we use the ratio proportional to find it, and so we just put everything in the calculator. Right, so just that. Next, so we have the Bermuda Triangle. I'm not going to write down all of those details, just trying to do the graph. So the Bermuda Triangle from Fort Lauderdale, Florida, very close to Miami, and then Bermuda, and then San Juan, Puerto Rico, So that will form a Bermuda Triangle. And then we asked to find the area. So let's read the question. And if the angle formed by the line of sight from Fort Lauderdale to Bermuda and to San Juan, so this angle is 67 degrees. And the distance from Fort Lauderdale to Bermuda, 1026 miles. And then the distance from Fort Lauderdale to Bermuda is 10. Wait, we have that. And the distance from Fort Lauderdale to San Juan is 1046. Now we're trying to find the area. So in this case, what we have is the side, the size, and the angle in between. So the area, it will be easier if we just assign the letters for the angle. So let's say A, B, C. Opposite to this, so this is little c. Opposite to this, so this is little b, and angle A. So the area is 1/2. We have to use angle A. So 1/2 BC sine A. So 1/2 B 1046 C 1026, and angle in between 67 degrees, right? Make sure it's in degree mode because we have degrees, so change that to degrees. And 1/2 or just type 0.5. (1046) times 1026 times sine of 67 is in degree mode. So when we do that, we have 493,941.1. Let's say this is square smile. That is the area of the Bermuda Triangle. So not much in this section. Just want to go it briefly so you know that the area of triangle, not only 1/2 base times height, but we can use a lot of all other things. Right. Now with that, we go to section 9.1 and 9.2. Man. Right, that will do. Section 9.1 about polar coordinates. And section 9.2 It's about polar equation. We also will not go over a lot of details in these two sections. Right. Polar coordinates. Right. Definition. In a polar coordinate system, we start with a fixed ray, and this is the ray, so not the whole line, just half of a line, called polar axis. And that is in two-dimensional space or in a plane. And the endpoint O is called the pole. Or equivalently in the Cartesian or rectangular coordinate called the origin. Just going to write out the definition first, and then we'll try to write a point P other than the pole. Can be determined by radius r. Radius r and array with vertex x. Vertex O that makes an angle theta with the polar axis. Right, we draw a lot already. We write a lot already. So first, I'll try to draw a triangle. I mean, in this case, the radius r, and so as always, when we draw a triangle, just hold this steady with the finger in between, and hold that so that will be very fixed. Will not move at all. What we move, we just move the paper. So the center is fixed, the radius is fixed, and we just rotate the paper. Do not rotate the hand. The hand have to be very steady. In that case, we have a circle. Good enough. We don't have a center as well. So let's say we have that. So in this case, we will not have the x-axis and the y-axis anymore. What we only have is the axis what we call the polar axis. And the radius r. So from the center. And then next, we will have an angle formed with the polar axis. So we have the polar axis, and then we rotate an angle. So in which case, this is a point P. We have two components. The first one is the radius. Second one is the angle theta. So any point given as the radius and the angle is called the position in the polar coordinates, which is what we have over there. So the other pair of numbers on theta are called the polar coordinates. Of P. Right. Notice that so we always have the polar axis, and then if we have a ray, if we go along the rays, that is the positive r. If we go the opposite to the point here, this point, because we go opposite direction of the ray, it is going to be negative r. The distance still r, or the radius, and the angle is the same. So if we have an angle, but rather than going with the terminal ray, we go the opposite direction, then we have negative r. That's what we have. So that's the second part. If we have r greater than 0, it will be on the same side as the terminal ray. Now, sorry, I make a typo on the note. If r is less than 0, it will be opposite of terminal ray. And if r equal to 0, we have the port at the pole. Right, so positive in the same direction as the terminal ray, negative on the opposite direction. C. Multiple representation of points in polar coordinates. Unlike rectangular coordinate, when we have x and y, if x and y are unique, then the point is unique. And the point is unique, we have a unique pair of x and y. That doesn't do anything. Trying to change the line. Right, now, what we have instead is if a point P has polar coordinates or in theta, then for any integer n, the point P can be represented as right. First, we have the radius the same, but the angle we can use coterminal angle, which is 2n times pi, and so this gives us coterminal angles, and coterminal angle have the same terminal ray, therefore the point will be the same. Right. Or if we use negative radius, then we have a point across from it. So if we add 180 degrees or pi, we go in the opposite direction. So this is opposite direction. And then we also have coterminal angles. Right. Let's go to the sample and see how it goes. Sample. I will modify the problem by a little bit. I'll find two more representation. First of all, let's sketch the point. Two and pi over 3. I will do that first, and after that I'll find two more representation. One with positive radius, and one negative, and one with negative. Radius. For 2 and pi over 3. Right, now first we have to draw it. It will be slightly problematic. First, usually when we draw the polar coordinate, we need concentric circles, and it will be very difficult to do that without compass. I don't know what happened to my compass. I left that in my office and school clothes. Right. So again, have to hold very steady. This time a lot more difficult. Right, so we have one circle. So this circle, radius 1. Now I'm going to draw the circle of radius 2. Too much. As long as the hand is steady, rotate the paper. Right. And this is radius 2. Let's do one more. Right, steady hand. Right. So we have concentric circles of radius 1, 2, and 3. Of course, we can do more or less. Next, this is the radius is equal to 2. So we know that it's going to be on the second circle, radius 2. And then the angle is pi over 3. Pi over 3 is 60 degrees. So I actually have a projector here. So that's 0 and 60 degrees right here. Connect that to the center. So what we have here is the terminal ray. On that, we have the point. Radius is 2, the angle pi over 3. Right. So that is the point 2 and pi over 3 right there. Pi over 3 is 60 degrees, so that's what we have. Right. So that's the first part. We sketched the point, which is good. Next, find two more representation, one with positive R and one with negative R. So it's very easy. First, let's do with the positive R. Now, if we have R is positive, meaning that we go in the same direction as that. So the radius is going to be still 2. The angle though, we can add 2 pi to get back to the same thing. So where we add 2 pi to it, when we add 2 pi to it, we're going to have a coterminal angle. And coterminal angle have the same terminal rate. So we have the same point. So this is one representation. 2 pi plus 3, 2 plus 1/3 is 7/3. So we can say 2 and 7 pi over 3. That is where we choose R to be positive. Now if R is negative, we have to go the opposite direction as the terminal ray. In which case, we have to write down the angle here. Right. So, if we take R to be negative, but still have to be in this circle, so it's going to be negative 2. So if we go negative 2, it's going to be in that. But remember, if we go in the opposite direction, and we start with a point here. So if we go -2, and go in this direction, and then we have to go back. So in that case, if we go with -2, we have to go with an extra revolution. So in that case, add a pi, right? So we have -2, and so add that for pi/3. Right, first, why do we have to add pi? Add pi to it, we have the point opposite is this. Right, so now think about this. If we go for pi/3, if radius is 2, it will be this point. So let me write this. If we have 2 for pi/3, it will be this point because we go an angle. This is the terminal rate. But if we want to go opposite direction, we throw the negative. So get back to the same point. So bottom line is, if we want the same point, add 2 pi or multiple of 2 pi. And if we want the opposite negative radius, we go the opposite angle and then go the other way with the negative radius. So that would be that. 2. So if we go to an opposite side, then have to go an opposite again, like an opposite of an opposite, we get back to the same point. Right, second part. Converting between polar and rectangular form. Right, first, let the positive x-axis in the rectangular corner is the same as the polar axis. So first, I'm just going to summarize this. We're going to let the positive x-axis be identical with the polar axis, which is what we have been doing. And in that case, the origin is the same as the pole. Then, right, before we do anything, if we can draw it, it'll be very easy to do. Right, first, just one portion of a circle. So first, the polar axis is the same as the positive x-axis. So this is the polar axis, or also the positive x-axis. And then the other one is don't have any particular name for it. Let's say we have a terminal ray angle theta. So we have the radius it will be very misleading if we write R right here. So right, so the radius and the angle, and so this point here is R and theta in polar coordinates. Right, what we do after that is we say this point, if we draw the right point here, this is opposite, which is y over r. I mean just y. Sine is y over r. So this is opposite the y values. And this here that is the x values. So this point is that given with radius and the angle, we can say this point is also x and y. So x, y coordinates, both of them, the point will be the same, but just different representation. Right, now it's not that difficult with the ratio. We define sine is y over r, and cosine x over r. Now multiply r on both sides. We have y equal to r sine theta, and x r cosine theta. And also in this triangle we have the Pythagorean theorem, r, which is x squared plus y squared equal to r squared. Or we can write r equals square root of x squared plus y squared. And also we have tangent is y over r, and if we take the inverse, tangent theta is y for x, or theta tangent inverse y over x. I'm going to put the asterisk here because something we need to worry about. So bottom line is we have this y equal to r cosine theta and x equal r sine theta. Sorry, r y equal r sine theta and x equal r cosine theta. Pythagorean theorem, r equals square root of x squared plus y squared, and then tangent is equal y over x. Next, right, there's an asterisk here. The point here is make sure that this is in the right quadrant. So just say make sure we check the quadrant. Right. Example. Convert the following points from polar to rectangular coordinates. Polar coordinates have r and theta. Rectangular coordinate have x and y. Right. So let's look at the first example. We have the point 2 and negative 30 degrees. Got some look for the hand. By now you should know all the values already. Right, so first, so in this problem we are given the point in polar corner. So this is R and this is theta. And very straightforward. To convert this into x and y, we have x equal to R cosine theta. So x is 2 cosine of negative 30 degrees. Cosine is an even function. Cosine of negative is the same as cosine positive. Just take the negative away because cosine is an even function. And cosine of 30 degrees, 3 fingers on the left, square root of 3 over 2. So we have square root of 3. That is x. And then next, y equal to r sine theta. R is 2 sine of negative 30 degrees. Sine of negative is a negative of sine because sine is an odd function, so this will turn to negative. And sine of 30 degrees, 1 finger on the right, square root of 1 over 2. So this is negative 1. So, yeah, just that. We have the coordinates x equals square root of 3 and y equal to negative 1. Right, so pretty much that. However, just make sure that this is correct. At least try to sketch to see if this is correct. Right, so in this case we have x equal to square root of 3 and y equal to negative 1. So the point is here. So, and also we have the point is equal to 2 and negative 30. So this is 2, the radius is 2, and the angle negative 30 degrees. So that check. The radius is 2. Yeah, so either we have x and y coordinate, or we have the r and then the theta. Both of them give us the same point. Right. Next, negative 4. And pi over 3. And this one, of course, also given in r and theta. So x equal to r cosine theta. Negative 4 cosine pi over 3. Pi over 3 is 60 degrees. And cosine, so we have 1 finger on the left. So 1/3. I mean, square 1 over 2. And y r sine theta. negative 4 sine pi over 3 square 3 over 2. 4 and 2 cancel, negative 2 square root of 3. So if we try to sketch negative 2, see about that much, and negative 2 over pi over 3, so about this much. So we'll talk about this point here. So the point we have is x equal to negative 2 and y equal to negative 2 square root of 3. Right. However, what we do in the polar coordinates is that we go to pi over 3 and then the radius, rather being in this direction, we go opposite direction, negative 4 the other way, and we have the same point. So we can write negative 2 square root of 3, or we can say negative 4 pi over 3. So either that or that. This one in polar, this one in rectangular. They both represent the same point. Now let's do this in the opposite, in the reverse direction. Now we change from rectangular to polar coordinates. Rectangular will have two coordinates x and y, and polar is r and theta. So we go from xy to r and theta. Right. This problem we definitely have to draw it and make sure that it is correct. So first 2 square root of 3. So this is in rectangular, so x is equal to 2 and y is equal to square root of 3. First, to get to r, we're going to use that, and to get to an angle, we're going to use that. I don't have to do that because the knot over there. Much better. So we have r equals square root of x squared plus y squared. Square root of 3 square. Right. 2 square is 4. and square 3 square 3, so we have square root of 7. Right, next we have tangent of theta is y over x. So that means tangent of theta is y over x. This does not give us any nice values, but that is fine. When we solve for theta, just take tangent inverse. Usually if it is in using the inverse function, we keep the calculator in degree mode, which is good. It's already in degree mode. Tangent inverse of square root of 3 divided by 2. We have 40.89, so let's say 40.9 degrees. So in this case, what we have is r and theta, the point in polar coordinates. R equal to square root of 7, and then the angle is 40.9 degrees. If we sketch this, two, and then square root of 3. So at that point there, 2 on the x, square of 3 on the y-axis, and the angle here is about 40.9 degrees. So that looks good. Next, convert the point -3 and -3 to the polar coordinate. So this given in the rectangular coordinates. So we have x equal to -3 and y equal to -3. So we write r equal to square root of x squared plus y squared. Square root of -3 squared and -3 squared. 3 squared is 9, and that is square root of 18. Or we can say square root of 9 times 2, or square root of 9 times square root of 2, which is 3 square root of 2. Next we have tangent is equal to y over x. Y is -3 and x equal to -3, which is 1. Now to get back to the angle, just take tangent inverse of 1. We have 45 degrees. If we want to, pi over 4. Right, now let's sketch. So we have the point -3 and -3. So points right here. Right. So that is the point we have. And there's a big problem, because we have 45 degrees. 45 degree actually is here. let's just say pi over 4. Which is not in the right quadrant. To get into the right quadrant, what we have to do is we have to add a pi to it. So in that case, we're just going to add a pi to it. So we have the right angle of 5 pi over 4. So the coordinate, instead of -3 and 3, we can write this one as r in theta. The radius is equal to 3 square root of 2. The angle is 5 pi over 4. So the note here is, if we take the tangent inverse, if it is not in the right quadrant, we have to add a pi to it to get to the right quadrant. So that is different when we have to take the tangent inverse. It does not always give you the right answer. Sometimes we just have to add a pi to it. So always check the quadrant. Make sure that is the right quadrant. What we have pi over 4 is in the first quadrant. It is not 3. So if it's not right, add a pi to it. D. Let's keep that for a moment. Example. Convert an equation from polar to rectangular form. Right. Let me just write down the problem first, and then we look over that with the formula next. So the first one is r equal to 3. The second one, r equal to cosecant theta. Number 3, theta equal to pi over 4. Number 4, r equal to 2 cosine theta. Right. I go to the formula here. See. So formula is there. Right. So equation from polar meaning we have r and theta, and then rectangular meaning that x and y. So somehow we change this equation to the equation that have x and y in it. We're done. Right. So first thing we have r. So and r equal to square root of x squared plus y squared. Equal to 3. Easy enough, right? Replace r with square of x squared plus y squared. Square both sides. We have x squared plus y squared equal to 9. And for this one, the graph of that is r equal to 3, meaning the radius is equal to 3. So we have a circle, radius of 3. Right, so that's the first one. Next, r equal to cosecant of theta. We can replace r equal to square root of x squared plus y squared, but then the cosecant, that is the problem. So first, I just say cosecant, by the way, is 1 over sine, right? Over 1. So let's cross multiply. We have r sine theta equal to 1 when we cross multiply, and an r times sine is equal to y, right? So y equal to r sine theta. So this equation is y equal to 1. So what we have here, the graph of that is the line y equal to 1. So we try to somehow change from r and theta to x and y. There's a lot of different ways to do it. If it is equal to constant, just go ahead and replace r with square root of x squared and y squared. If there's a trig function, somehow have to utilize that properties, and so we can change to x and y that way. So what we have here is this. So theta is equal to pi over 4. So what I do is I'm going to take tangent on both sides. Tangent of theta, we can replace that with y over x. And tangent of pi over 4, tangent of 45 degrees is 1. Cross multiply y equal to x. And y equal to x is the diagonal line like this. The last one is a little more difficult. Notice that if we have r times cosine, that will be x, r times sine will be y. Here we have cosine by itself. We cannot move the r to the other side, because if we move the r to the other side, that is dividing and not multiplying. What we do need is r times cosine though. So what we do, why don't we multiply r on both sides? R times r square, and then move the r cosine to closer together like that. And r times cosine is x. And so we have r square, r is square root of x squared plus y squared, so r squared is x squared plus y squared. Right, so we have this. We have to do the completion square to turn that to the equation. By the way, if we want to graph it, especially the equation in terms of r equal to, we can graph using the calculator. Right. If we want to graph it, we need to set a few things. First, in the radian mode. Right, first thing. Second, we have to change to the polar. So radian and then the polar mode. And then we can graph. Let's say r equal to 3, and then we have the graph. By the way, it does not look like a circle, even though we have 3 up and 3 down to 11, right? If we want this to be like a perfect circle, we have to hit zoom number 5. So in that case, we have 3, the scale on x and y will be the same, so that's the circle. Right, we cannot really type that because the equation is just r equal to, we cannot type that. We can type the cosecant though. Cannot type cosecant, but we can type 1 over sine. And just hit that button. They have x, t, theta, and n. If it is in the polar mode, when you hit this button, automatically give us theta. And you have the line y equal to 1. And then how about this? R equal to 2 cosine theta. And so that is the circle. If we do the completion square, we will have the circle here, raised there. Right. And then we can do something very nice. For example, if I put 6 here, and then I put cosine of, let's say, 7 theta. And let's see the graph. It's not very nice, right? So, let's do this again. 10 cosine of 3 theta. So it will have a rows with 3 petals. Now if we have 5 petals, just change this to 5. So if it is an odd number, it will graph, and that will be 5 petals. Now, if we put an even number, it will double the number of petals. If we put 2, it's going to be 4 petals. 1, 2, 3, and 4. So, again, mode, make sure it is in the polar mode. And when we graph it, this is from 0 to 2 pi. We actually can change how close we are. So we, minimum is 0, and then 2 pi. And then the step, we can say we want to graph from 0 to pi, divide that into 100 points. So it will go very slow, but the graph will be very smooth. Right, so that's what we can graph the polar coordinates. Now we do it in the opposite direction. Now convert an equation from from rectangular to polar. So don't get there yet. Example. Right. Convert an equation from rectangular to polar. Rectangular is x and y. So we are given x and y. We just need to change to polar, which is on theta. Let me write out the problem first. Y equal to 2. Y equal to x squared x squared plus y squared equal to 25. 2x plus 3y equal to 5. Right, so y equal to 2. Right, what do we have about the polar? Sorry, let's go to the formula first. That. One more. Right. So y, we are given y. Need to change this into r and theta. That's easy. Y is r equal to sine theta, right? And then if we want to solve for r, just go ahead and divide by sine theta on both sides. So we have r equal to 2 over sine. Reciprocal of sine is cosecant. So we have r equal to 2 cosecant of theta. So as long as we have the equation in terms of r and theta, we're good, and that's what we have. Right, next, y equal to x squared. Similarly to what we have on that side, y is equal to r sine theta and x equal to r cosine theta. We have a square. So r sine theta equal to r squared to the r and the square to the cosine. Right. Both of them have on one side, so let's divide by r. So we have sine theta equal to, cancel out, r cosine square of theta, and divide by cosine square on both sides. We have r equal to sine divided by cosine square. Right. Next, x squared plus y squared equal to 25. Now this one is obvious. If r equals square root of x squared plus y squared, so x squared plus y squared is just r squared. If we want to take the square root on both sides, that's perfectly fine. So we can have either r equal to plus or minus 5, but just take positive. By the way, if r equal to negative 5, that's perfectly okay too. Next, we have x and y here. We need to change to r and cosine. So x is r times cosine, and y is r times sine. There's a 2. There's a 3. So we just have 2r cosine theta plus 3r sine theta equal to 5. Actually, this is good enough as because we do have in terms of r and theta. Now, if we want to scrambling around, factor out of r, 2 cosine theta, 3 sine theta, and then divide by that. So if r equal to 5, 2 cosine theta plus 3 sine theta. Right. Once again, rectangulars x and y, polar r and theta. We can change from r and theta to x and y, interchangeable. So make sure we know how to do that. Next, we have symmetry in polar coordinates. Let's look at which one. So there will be three types of symmetry. First, symmetry with respect to the polar axis. Right, so let's just try to sketch this real quick. We have the polar axis, this one. What we have is symmetry. A point here is on theta. Symmetry across the polar axis. What we have is just the same radius, but the angle, instead of clockwise, counterclockwise by default, we go clockwise in the opposite direction, negative direction. And so those are the relation. So in this case, in order to get the symmetry with respect to the polar axis, what we do is, if we replace theta by negative theta, and we obtain the same equation or equivalent. Next, symmetry with respect to the line y equal to pi over 2. Try to draw this again. What we have here is the line y equal to pi over 2. And we still have the polar axis here. So if we have the point here, we would want to know the point opposite to it. And we're trying to find this point. Right. By the way, the point here obviously the same radius, but in terms of the angle, what do we have? So if this is angle theta, that much, then this also the same angle and go counterclockwise rotation. Now what we actually want is this angle. So if this is from here to here is theta and the whole line is 180 degrees or pi, so this is going to be pi minus theta, or the supplement. So this is the opposite, this is the supplement. So if we want this symmetry, what we need is replace theta by pi minus theta. When we do that, and we obtain equivalent equation. Usually if it's just cosine, it works. If it's just sine, it will work, because sine is a supplement and cosine is opposite. We see that on chapter 6. C. Symmetry with respect to the point. And the point is also the origin. Right. Right. Actually, if we have a point about here, we're trying to go to the opposite direction. To the point here. So how do we represent that in terms of the polar coordinates? So there are two ways to do it. One, we're going to keep the radius, and one we go with. Want to keep the angle, by the way. First, if this is angle theta, and since this is opposite direction, so we do is just we throw in the r, throw in the negative to r, and this is one representation of the point. Right, so that is first. Or if we don't want to do that, in that case, let's just go this angle, and that angle is pi plus theta, and then we're going to go with r. So there are two representations for the same point, either negative r and theta, or r and pi plus theta. So those are the two representations of the same point. So in order to get that, we'll replace r by negative r, or replace theta by theta plus pi. When we do either one of them, we obtain equivalent equation. Right. So so those are the three types of symmetry in polar coordinates. And that is the end of section 9.2. Now we go to section 9.3, complex number. Right. Later on, we will use trigonometry related to complex number, but here we just do the complex number algebraically, so there's no trigonometry involved in this yet. Definition. So there will be quite a few things here. First, remember we define that the square root of -1 is called I, the imaginary unit. So we define square root of -1 is equal to I. If we square both sides, we also have I square equal to -1. Right, so I is equal to square root of -1. So we define. Next, a complex number is in the form z equal to a plus bi, where a is called the real part of z, or we can say the real part of z is equal to a. B is the imaginary part of z. Or if we write imaginary part of z is equal to b. By the way, what is a and b? A and b are real numbers. If a is equal to 0, so in that case d is equal to bi, and so we just say pure imaginary. If b is equal to 0, so z is just equal to a, which is a real number. So complex number is in the form of a number plus b, another number times imaginary. For any positive number b, so b is positive, this highlight is even more difficult to see. So negative square root of -b equal to, so first, if we have a negative inside the square root, that will be the imaginary I on the outside, and will remain have square root of b. So just that. And number 5. By the way, those are Roman numerals in the lowercase. Two complex number equal if and only if the real part are equal and imaginary part equal. By that, I mean the real part equal to real part, imaginary part equal to imaginary part. So, for example, if we have z equal to a plus bi and w equal to c plus di. When we say z equal to w, if and only if a is the same as c and b is the same as d. Next, operations on complex number. For real numbers a, b, c, and d. Let's say we have two complex number. Let z be a plus bi and w be c plus di. And first we have the sum. Z plus w. Now if we write z as a plus bi and z as c plus di, when we add them, just combine like terms, a plus c, a plus c, and then b plus d. I'm sorry. Two. Difference. We just add them, number by itself and I together. So pretty much combine like terms. Difference. Now we subtract. We subtract them. So a and c, so a minus c, and then b and d with I. So a and c with the minus in the middle, b and d with the minus in the middle, and then factor out the I. So pretty much just combine like terms. Next, product. Z times W. Notice that I do not put a dot in between them, just Z and W. So we have A plus BI and C plus DI. Now we will multiply out AC plus ADI BCI and BDI square. Just multiply it out. Next, I square is -1. So we can write this as AC plus ADI. Run out of space. So let's try to put that here. It's not ideal, but should write that on the next page. Anyway, let me write this again. Product Z times W A plus BI C plus DI AC plus ADI BCI, just like alphabetical order, BC and then I, and then BD I square. I square is -1. Substitute this back, we have AC plus ADI plus BCI, and then I square is -1, so we just have minus BD. And then finally we put the real part together, AC minus BD. And then the imaginary part together, AD and BC. Right. By the way, formulas is nice and all, but we don't even need the formula to do this problem. Right. So first let Z equal to 2 minus 3i and W 4 plus I. Now find Z plus W. I said we don't even need any formulas to do this problem. Just substitute in 2 minus 3i for Z, add 4 plus I for W. So 2 minus 3i, then plus 4 plus I. Remove the parentheses. Now combine like terms. 2 plus 4, the real parts, 6 minus 3i plus I. So just like that. No need for formulas. 2. What if we want to multiply them? Then we just multiply them. Two minus 3i and W 4 plus I. Now multiply it out. 2 times 4 is 8 plus 2i minus 3i times 4 minus 12i and minus 3i squared. So we just multiply it out like FOIL I squared is negative 1. So we replace to that 8 plus 2i minus 12i minus 3 and I squared is minus 1. So I have 8 plus 2i minus 12i, that minus 10i. And then minus 3 times minus 1 plus 3. So this is 11 minus 10i. By the way, we can use a calculator to do this. If we have a TI 83 or 84 heat mode and go down where say we have real numbers or imaginary, I will go to the a plus bi, the complex in the form of a plus bi. Right, in that case we just type exactly what we have. First 2 minus 3, the I is here, second decimal point, and then we plus 4 plus I, 6 minus 2i. If we want to multiply them, 11 minus 10i. So calculator knows that as well. Number 3. Negative I z plus 2w negative I z plus 2w. Right, I just multiply it out. Minus 2i minus a negative plus 3i squared plus 8 plus 2i. Of course we can do a lot, but conveniently 2i, negative 2i cancel out. I squared equal to negative 1. So we replace to that. We have negative 3 I squared negative 1 plus 8. So that is 5. So do we have 5? So we have I times 2 minus 3i plus 2 4 plus I. So that, wait. Forget the negative here. Second, insert, put the negative in front of it, and that's what we have. So kind of straightforward. Just combine them, combine like terms. I squared is negative 1. That's the only difference here. B. Example. Evaluate I cube, I to the 4th, I to the 5th, and so on. Right. Let's just write out what we need, what we have. Sorry. I to the 0 power anything raised to 0 power is 1. Now I to the first power, by default, anything raised to the first power is itself. I square, by definition, this is -1. I cube, to get to a cube we have I to the first power times I square. I to the first power is I square is -1, so this is -I. Right. Because I know the answer already, so I just keep writing here, skip a line here. I to the fourth power is I square times I square, which is -1. I should not do that, but it's still 1. I to the fifth, I should just say I to the fifth is I to the fourth times I. I to the fourth is 1 times I is I. I to the sixth, I to the fourth times I square. I to the fourth is 1. So just I square is -1. And I to the seventh is I to the fourth times I cube. I cube is -1. Sorry, I cube is -I. So we have -I. So if we just keep doing that, as you see the pattern repeating, 1I, -1, -I, 1I, -1, -I, and just keep repeating. So if we want to go to I of 100 power, and that will get back to 1. So we can add, we can subtract, and we can multiply. Next part is how do we divide. For complex conjugate. And quotients. Of complex numbers. Right. First definition. If z is equal to a plus bi, then the conjugate we'll call the complex conjugate. Of z is denoted z bar, and we define as follow, and define by a plus bi equal to a minus bi. So the real parts remain the same. The real part remains the same. The imaginary part turn to opposite. So what is the significance of that? Let's first find the product of conjugates. By the way, when we write like this, we can also write when we have A minus BI, when we do the complex conjugate, we end up with A plus BI. So again, the real part remains the same. Imaginary part turn to opposite. So if we have Z equal to A plus BI, then the product of a number and its conjugate so we'll just multiply it out. A square minus ABI plus ABI minus B square I square. I square is equal to -1. So we have A square cancel out, a negative B square, I square is -1. So A square plus B square. So let's just say the product of the number and the conjugate is equal to the square of the real part plus the square of the imaginary parts. Now we divide them. If we have W divided by Z, we define as W over Z. What we do is we will multiply by the conjugate of the denominator, top and bottom. And of course, that's not finished. Just simplify after that. We'll see when we have a particular problem. Right. Let's see some example here. Let Z equal 2 plus 5i and W 3 minus 2i. Find our first conjugate of Z. The conjugate of Z is the conjugate of 2 plus 5i. Have the bar on top. The real part stay the same. Imaginary part turn to opposite. Next, W times conjugate of W. Second example. W 3 minus 2i and the conjugate of W is 3 plus 2i. So we just change the sign of the imaginary part and then we have it. Right. Just multiply it out. Even though we know it's going to be 9 plus 4, so 13. But just multiply it out. This is something that we don't need to memorize. 3 times 3 is 9. 3 times 2i, that will be 6i. Negative 2i times 3 minus 6i. And negative, so that's negative 4 I squared. And once again, I squared is negative 1. Also 6i cancel out. So we just have 9 minus 4 times minus 1. So 9 plus 4, 13. W divided by Z. Alright, now this is a little bit different. So let's just put the number first. W is 2 plus 5i. And W is 3 minus 2i. Right? Of course, I put them backward. Sorry. Three minus 2i for W, and Z 2 plus 5i. Right. So what we do is we multiply by the conjugate of the denominator. So just change the sign of the imaginary part. Now just multiply it out. Three times 2 is 6. 3 times minus I minus 15i minus 4i minus negative, so plus minus minus, so that's 10i squared. 2 and 2, 4. 2 is minus 5i minus 10i plus 10i minus 25i squared. So we have 6 minus 15 minus 4 minus 19i. I squared is negative 1. That cancel out. 4 minus 25, I is negative 1. 6 minus 1 minus 16 minus 19i. And 4, 25, that's 29. Actually, here we're going to split negative 16 over 29 and then minus 19 over 29i. Why do we have to split like that? Because the result, we need to write this as a real part and imaginary part. So let's say we divide them. 3 minus 2i. Is that still in complex? Yes, a plus bi. So we have 3 minus 2i. And then divided by 2 plus 5i. Right. We can change the fraction. So next way. Yeah, that's why we need to check, right? 6 minus 10 is minus 4. Minus 4 over 29 minus 19 over 29. Alright, so we should give the answer in the form of complex number, real parts and imaginary part. So W divided by Z. Next, we find Z divided by conjugate of W. Right. Z 2 plus 5i conjugate of 3 minus 2i. 3 minus 2i is W, and we have the conjugate of that. So, the conjugate of that turn the negative, turn the imaginary part to opposite. This is negative I, turn into positive. Negative 2 to positive 2. Right. And when we divide, we just need to multiply by the conjugate. We just multiply W top and bottom, which is just fine. But the conjugate of this is three minus 2i. The conjugate of the denominator, we have I is imaginary, turn that to opposite. We have 2 as imaginary, turn that to opposite, negative 2. The real parts must be the same. Right, and then we just multiply it out. 2 times 3, 6. 2 minus 2i minus 4i plus 15i minus 10 I squared. And then at the bottom, 3 times 3 is 9. 3 minus 2i minus 6i. 2i times 3, 6i. And 2i minus 2i minus 4i squared. Six. Minus 4i plus 15 is plus 11i. And I squared is negative 1. 6i and 6i cancel out. We have 9. And I squared is negative 1. So we have 6 minus minus, so that's 10, and 6, so that's 16, plus 11i. And then 9 plus 4, 13. And we will split 16 over 13 plus 11 over 13i. Sorry, looks like there's something wrong with the camera. Should be fine. Right. So we have 2 plus 5i divided by 3 plus 2i. And convert this to fraction. 16 over 13 and 11 over 13i. Right. So with that, we finish section 9.3. Once again, I have to do some offline video because the class time is not enough for us to cover everything. But now we're back on track. As always, thank you for watching.